Hi everybody, I am Professor Jesus Toribio from the University of Salamanca in Spain. The title of my presentation is Anisotropy of Hydrogen Embrittlement in Cold-Drawn Pyrolytic Steel, attribute to Mantegna. I am with the Fracture and Structural Integrity Research Group of the University of Salamanca in Spain. First of all, the outline of my presentation. I am going to divide my speech into 6 parts. Introduction. Second, cold drawing of pyrolytic steels. 3. Microstructure evolution during cold drawing. 4. Consequences of cold drawing on crack paths. 5. Hydrogen-assisted cracking paths, HELP versus HEDE, hydrogen-enhanced localized plasticity versus hydrogen-enhanced decohesion. And final part, linking with art, resembling Mantegna's Dead Christ perspective. Let's go to the motivation of this research work. The motivation is based on the fabrication of high-strength precision steel wires by cold drawing. This produces a progressive orientation of the 2 basic microstructural levels of pyrolytic colonies and lamella. And as a second effect, it creates an influence on the fracture and structural integrity. Then the aim of the work is to analyze the influence of cold drawing degree on the hydrogen embrittlement performance of cold drawn wires. And this is a fraction mechanics approach to the design of pre-stressed concrete structures. Let's move to the second part of the presentation, a description of cold drawing of pyrolytic steels. Cold drawing of pyrolytic steels is produced by progressive cold drawing, consists on passing of the pyrolytic steel wires through several dies. It creates a clear increase of yield strength and ultimate tensile strength by a strain hardening mechanism. Here we have a schematic picture of the wire passing through different dies of decreasing diameter. Here we see from initial diameter D0 passing through the first, second, third, fourth, fifth, and sixth die with 1, 2, 3, 4, 5, 6 reductions of diameter and progressive increase of the yield strength by a strain hardening mechanism. In the bottom of the slide, we have a 3D picture of the manufacturing process by cold drawing. We can see the wire passing through the dies manufactured by hard metal. Third part of the presentation, here we can see the outline, microstructure evolution during cold drawing. This pyrolytic steel has 2 microstructural levels. The first microstructural level is the pyrolytic colony. Here we can see the evolution of pyrolytic colonies with cold drawing. In this slide, the horizontal side is the radial direction and the vertical side of the micrographs corresponds to the axial direction or y-axis or cold drawing directions. We can see steel 0, hot roll base material, not cold drawn at all, on the left-hand side of the slide. In the middle we can see steel 3, intermediate degree of cold drawing, and in the right-hand side we can see steel 6 with the highest degree of cold drawing, heavily drawn pyrolytic steels. Regarding the colonies, we can see in the steel 0, left-hand side of the slide, are randomly oriented pyrolytic microstructures. All the colonies are randomly oriented and they are more or less a circular shape. In steel 3 we have a clear enlargement and slight orientation of the colonies in the vertical direction of the micrographs in the y-axis or cold drawing direction. Finally, in the right-hand side of the micrograph, steel 6, heavily drawn steel, commercial precision steel wire, we have a clearly oriented microstructure with extremely slender pyrolytic colonies, slender in the drawing directions and oriented also in that drawing directions. With regard to the evolution of pearlitic lamella, second microstructural level, again we have in the left-hand side still 0, whole roll material, base material, not cold drawn at all, still 3, intermediate degree of cold drawing in the middle, and in the right-hand side still 6, heavily drawn pearlitic steel, pre-stressing steel, cold drawn white after 6 drawing steps. In steel 0, we had the boundary of the colony. A colony is a set of ferrite perlite lamella, ferrite cementite lamella with common orientation and different orientation from that of the neighboring colonies. We have a random orientation of both the colonies and this second microstructural level, the lamella. In steel 3, we have a slight orientation of the lamella, and finally steel 6 exhibits the highest degree of orientation, the most heavily drawn material, with a clearly oriented microstructure. Is like a composite material, plated material, oriented in vertical direction, the plates, ferrite cementite lamella, and with a compact structure with decrease of pearlitic interlamellar spacing. Then the summary of microstructural evolution during cold drawing, we have, regarding the first microstructural level, a progressive orientation and slenderizing of the pearlitic colonies, first microstructural level. With regard to the second microstructural level, progressive orientation again of the perlite, ferrite cementite lamella, second microstructural level, and decrease of interlamellar spacing, an increase of packing closeness. Then, as a summary, we have orientation of the two microstructural levels in the drawing direction and increase of packing closeness. Let's go to the consequences of cold drawing on crack paths, fourth part of the presentation. Here we have the fracture profile in hydrogen-assisted cracking from slightly drawn steels in the left-hand side of the slide, middle part with intermediate degree of cold drawing to the most heavily drawn steels in the right-hand side of the slides. In slightly drawn steels or hot rolled material, we have fatigue propagation in mode 1. After the fatigue pre-crack, we have final fracture by cleavage. After the fatigue pre-crack, we have a subcritical mode 1 propagation, hydrogen-assisted cracking, and final fracture by unstable fracture by cleavage. In the middle degree of cold drawing, we have a slight propagation by mixed mode with a slight component of mode 2 and final fracture by cleavage. And in the most heavily drawn steels, we have a clear deflection or deviation of the cracking angle with a clear component of mode 2. This is at the top. At the bottom, we have the fracture profile of the progressively drawn steels, and we have a progressively anisotropic hydrogen-assisted cracking behavior with cold drawing, with an increase of the angle of propagation from 0, 1, 2, 3, 4, 5, 6. An explanation of this lies on material anisotropy. We have strength anisotropy, mechanical anisotropy. K1C depends on the propagation angle. For a 0 angle corresponds to fibers fracture, transverse fracture. And K1C parallel, or K1C for a theta angle of 90 degrees, we have longitudinal splitting or delamination. Then K1C perpendicular for fibers fracture, transverse fracture, is quite higher than K1C parallel for delaminations parallel to the fibers, or to the plates. In addition to this, we have chemical anisotropy for hydrogen diffusion, D perpendicular, the hydrogen diffusion coefficient for transverse direction in the initial crack direction, perpendicular to the fibers, is D perpendicular. And we have D parallel in 90-degree direction for a deflection angle of 90 degrees for a direction perpendicular to the initial fatigue crack. We have diffusion in the longitudinal direction. Then we have diffusion D parallel is quite higher than diffusion in perpendicular direction. Diffusion is most favorable in the direction on the plates than crossing the plates. Here we have an schematics of the micromechanics of hydrogen-assisted cracking in progressively drawn pearlitic steels. In the most heavily drawn steels, we have preferential hydrogen diffusion in D parallel in the direction of the plates, the fibers, and lower fracture toughness in the cold drawing direction or fibers direction. Then, with this preferential diffusion, as a consequence, we have hydrogen-enhanced decohesion, delamination, or debonding HEDE between two similar microstructural units, colonies or lamella. Then, let's go to the fifth part of the presentation, hydrogen-assisted cracking paths, HELP versus HEDE. Hydrogen-enhanced localized plasticity versus hydrogen-enhanced decohesion. Here we have the mechanism for the lowest degree of cold drawing. Hydrogen-assisted cracking paths, HELP versus HEDE, in slightly cold drawn steels, or not cold drawn at all, like the hot rolled material, we have a randomly oriented perlite, and we have a fractometallographic analysis of crack paths. Fractographic analysis because we deal with fractured crack paths, but metallographic analysis because after polishing we can observe the microstructure of the material. Metallographic or materialographic analysis. The hydrogen-assisted cracking paths exhibits hydrogen-enhanced localized plasticity helped by the so-called tearing topography surface, a kind of tearing localized plasticity, and the crack path crosses the colonies and breaks the lamella. It's interlamellar and intercolonial. With regard to the most heavily drawn steels, the hydrogen-assisted cracking paths in commercial prestressing steels with oriented perlite shows an evidence of delamination, and in this case we have hydrogen-enhanced decohesion HEDE by a kind of enlarged and oriented TTS, EOTTS. We have the two different mechanisms, help in slightly drawn steels and HEDE in heavily drawn steels. Then to close the speech, sixth part of the presentation, resembling Mantegna's Death Christ perspective. Here we have the beautiful picture by Mantegna, a real masterwork, Mantegna's Death Christ. We define the MDCP, Mantegna Death Christ perspective. Why? Because in hydrogen-assisted cracking paths we have a strongly anisotropic behavior in heavily drawn steels, and regarding hydrogen-assisted cracking paths of this commercial prestressing steel, heavily drawn, we have a deflection deviation angle of 90 degrees to have propagation by fibers or plate debonding in the direction of cold drawing. Y-axis of cold drawing direction. This 90-degree deflection angle in the hydrogen-assisted cracking paths resembles the foreshortening perspective rotated 90 degrees in Mantegna Death Christ perspective, MDCP. That is the link between science and art, between art and fracture mechanics. That's all. Thank you very much for your very kind attention.